Okay. All right. Hi, everybody, and thanks for joining for another EERI seminar. Today, we've got Dr. Marianita Gutierrez Soto. She's an assistant engineering professor at Penn State. She's affiliated with the agricultural engineering and the civil environmental engineering departments at Penn State. She is also the director of the design of the Resilient, Engineered, and Autonomous and Multifunctional, or DREAM, Structures Lab. She got her bachelor's at Lamar University in Texas, and then got her master's and PhD in civil engineering at Ohio State. And she's also gotten quite a few awards and she got the 23 to 24 Faculty Engagement Award from Penn State's Teaching and Learning with Technology Center. Also got the Teacher Who Made a Difference award in 2020 and the Faculty Research Mentor of the Week in 2019 from the University of Kentucky. She's also gotten the Presidential Fellowship in 2016. With that, we're very excited to have you, Dr. Soto, and please take it away.
Thank you so much, Noah, for your great introduction. And I want to thank the EERI chapter for hosting me, as well as the University of Nevada, Reno, for this opportunity to share our ongoing work. I'm excited to share what we have going on in our lab. And I just want to, share really quick. Just as you mentioned, I am an assistant professor of engineering design, and I am affiliated in the architectural engineering as well as the civil and environmental engineering. And my experiences span from structural engineering, from field construction engineering, forensic engineering, human-centered design. But one thing that you may not have known is that I was actually a professional tennis player for a long time, and I actually played NCAA Division I, and that's what got me to go to Lamar. I had experience working at Turner Construction, building a hospital building, and recently I started getting involved since 2017 with this group called STEER, a Structural Extreme Events Reconnaissance Mission, where we deploy after natural hazard events and learn about what's happening to the built environment after something happens. So the question that I have presented in this talk is based on how do we design for the extremes, right? So how might we respond before, during, or after an extreme event? And these are the different strategies in which our lab has been looking into each of these hazards. So what can we learn from site visits after an extreme event? So I will pose that first question. And for those in the audience that may not be familiar with these organizations, I just want to do a brief introduction about these EERs. So these are reconnaissance networks, and the EER is the extreme events research, right? So you have the geotechnical group, the social science group, the nearshore extreme groups. And as you can imagine, after an extreme event, you also have to think about the disaster, the debris that is being created after the disaster, right? So that's where these sustainable material management, like how do you manage the debris after an extreme event? So, and there are groups that are near the coast, right? So coastal structures, so that's another focus. My experience in this space is that you also have the ICEER, which is the Interdisciplinary Science and Engineering Extreme Events Research, which is basically in the middle, unifying all the other EERs. And I left the link there in case you want to check out all of these different EERs. But then the one that I've been involved with is actually the structural focus, the STEER. So the STEER.network, if you haven't seen this before, is the idea that is building resilience to reconnaissance. So it's a network. This is sponsored by NSF. That you basically go and learn from these extreme events. And the way this works is that it's building capacity. It has coordination as well as collaboration. So this is not just for academics, but also other people that are involved in this space, right? So the idea is that as we're documenting what is happening, we can have a broader audience and disseminate widely from anyone that might be interested. So since it starts at 2017, there have been many different events that have been responded since then, event briefings, reports, and records that have been documented throughout the years. Now, the way this works, the response workflow, is that it can either be a major hazard that has little potential to generate knowledge, right? So when there's a big event and then the potential to generate new information is small, then we will deploy an event briefing. If there a potential to generate new knowledge, then we start with a preliminary virtual reconnaissance report, which basically relies on information that you can obtain digitally, virtually from the media, from social media, and so on and so forth. So things that we can assess without going in the field. And if there's a potential to actually gain some valuable information that is also new, then we will start responding towards an early access reconnaissance report, right? So we have these three different levels. An event happens, and so for example, Hurricane Helen, from last week, then we immediately created a VAST. So we're currently working on this virtual assessment, and depending on that information that we collect, we might be able to deploy some field teams so that we can gather some data and inform that information. And then eventually we do this curated data set so that everything is cleaned and is consistent. So what sort of information do we capture when we go on these field assessments? Well, we can either do a door-to-door assessment using the Fulcrum app. We can fly some drones over the sites to capture some information about the overall damage. We can also get Street View technology, right? So you mount these cameras over your car and you drive around to be able to capture and get a sense of what information has been gathered from there. Or you can do terrestrial scanning technology. So when you do this, you basically create a digital replica about a particular structure or something that for you think that will be meaningful, right? So when you fly a drone, you might not be able to get the resolution that you want on a particular structure, but when you have this combination of different technologies, that you can get an overall assessment of the damage. So this is the mixed methodology strategy, right? So you have some door-to-door, so you can capture some very punctual, relevant information, and with the UAS and the surface panoramas, you get an overall feel about what's happening, what is the broad extent of the pattern, and you can see where the damage took place, right? So the door-to-door assessment will look at the Fulcrum app. So it's basically using your own phone. You can download the app. And what you do is that you basically start documenting with your camera and maybe some audio and some free-form text to capture some information as you're seeing the damage in place. So we capture all sides of the structure and get some information about water-induced damage. If for some reason you have some storm surge, that you can capture the water level, and so on and so forth. So what's interesting is that we basically have a pre-deployment mission design. So we will have coordinated information with different teams so we don't duplicate data. And then we will have a team that might deploy to certain sites. We'll do some coordination. We look at representative samples. So we're not just capturing residential structures, necessarily all of them, but just some that we think will be meaningful information for the field. So we will have additional steps after the assessment to make sure that the information that we provide to the community is reliable, right? So we will look at the county records. We will look at structured for FEM models, the point clouds, right? We can look also at other sources of information, but you can see a variety of different data for data quality assessments for this. So this is just one example. Each dot represents the level of damage, right? So you can have minor, moderate, severe, or destroyed. And then from each of those data points, you will basically have an annotated picture about the actual damage was perceived in that particular location. And that's how we capture it. So a lot of this information will also upload it on Mapillary, which is like Google Street View, but it's actually Mapillary, and you're able to get access to different time lapse. So if you run your Street View today, you run the Street View, before, and so on and so forth. So Mapillary is another source where we upload that information. Design Safe will have some data sets. So you get here some information about the ground-based imagery, UAS technology. We also have the detailed reports documenting what we did, and also different information. So what's really neat is that once you have access to this community, you get access to all the records, and so on and so forth. So I can share with you my particular involvement after the tornado outbreak that happened in 2021. So tornado hit, and then one particular area that got affected was actually Mayfield, Kentucky. And one of the things that we noticed when we were looking at the site is that the areas that got impacted the most were actually historical structures. So the US Post Office was constructed in 1910, and there was actually no indication on the code on how these historical buildings actually performed during tornado loadings. So we started looking at some information and gathering additional data. So after we did the assessment from the tornado outbreak, we went back and captured additional data, and we received a rapid from the NSF to be able to have more information with regards to the performance of the historical structures. And these are just glimpses of the different damage types and damage typologies on the different structures that we were looking at, and the different data collections. So we have multimodal data, including laser scanning, photogrammetry, and drones. And then we have a whole team looking at the tags and how do we gather this information. We did the street view and being able to navigate different sources. So the way this works is that you basically capture this information, you put it on the software, and then you start looking at the images, and then you overlap them so you can get a digitized version of the software. So this is the reconstructed one from what you saw in the images. And then one thing we started developing in our lab is this Cloud to FEM. So it's an open source software that basically takes a point cloud and starts developing a finite element model based on the point cloud that you're gathering. And of course, one of the challenges when you do this kind of work is that depending on the quality of your cloud, your point cloud, then there are going to be some areas that you have to make some assumptions regarding with the material. So, some assumptions for ASCE, of course, like how do ASCE 722 look at tornado loadings for these particular structures, and the tornado speed that is estimated versus the site estimations, which is basically an estimation based on how the trees fell on the area and looking at the comparison between them. So we started looking at the stress concentration of the loading conditions, and then looking at the ASCE versus the ones that we actually estimated based on what we saw on the site. So there's also in this project will basically give us some information about how those historical buildings fail under extreme wind loading, especially when you start looking at retrofits and other types of additions, and what is actually creating that. So when we look at the variation parameters via simulation, we can also look and correlate, does the damage that we see in simulations correlate with what we saw on the site? So all this information is available. You're welcome to check it out. It's on the website for Design Safe, where it's a repository with a lot more information, not just this site, but for a lot of the EER. So all of the extreme events reconnaissance missions will have the data involved here. So you're welcome to check out this one, but also the other ones. Because this is EERI, I'm sure that many of you are familiar with the learning from earthquakes. So learning from earthquakes has been doing this kind of assessment after an extreme event for many, many years. And one thing that we did as part of STEER is that we wanted to have all the hazards in one place, not just earthquakes, because there's more than just earthquakes, and all of it is important. So having one centralized place to have this information was sort of like the vision for this STEER community. Now, if you want to know more information about earthquakes, of course, learning from earthquakes is definitely where you want to go to learn more about what's happening there. Another resource that I always find interesting that students really like to enjoy is learning about the disaster cities. So Texas has an area that actually, was impacted by an extreme event, and then they never rebuilt it because they actually left that city in place so that we have emergency responders trained in there. You can also do some research in these spaces if you're interested. But it's interesting because you have full-scale collapsible structures, you have different levels of simulations that you can do, and also that information is there for you to check out. Now, that is what happens after an extreme event. But the question is like, what are some innovative things that we can do before an event happens, and what have we done in this space? So we have done some contributions to the design standards. So one example includes this one right here. It's a diagrid structure. So diagrid buildings are buildings that look like this, right? So if you notice carefully, there are no vertical columns in these particular structures. They are being sustained by this triangular shape. So that's what called diagrid structures. And understanding the fundamental period of a structure is one of the critical parameters for earthquake design, of course, and estimating that fundamental period for these diagrid buildings is actually not in the ASE code. So we needed to go and study how these things actually influence the design. So that's one thing we did. Another two studies that we also are interested that we're looking at is these cross-laminated timber panels. But so if you're familiar with mass timber, it's a new construction material, relatively new. Many years have passed since it was like first tried out, but it's very popular nowadays to start thinking about cross-laminated timber. So the question in this project was looking at if you were looking at panels made of hardwood tree species, then how will they perform? So what are the structural properties of CLT panels made of hardwood species? So this is what this project is all about. And this one on the right is the one that looks most interesting, of course, because everyone is interested in additive manufacturing nowadays. But then can we predict the structural behavior when we start looking at the small to large scale applications? And if your new building is going to be built with these kind of lattice structures, then how will they perform, right? So that's sort of like the underlying question there. And since this is recorded, that you're welcome to check out the publications associated with this project to learn more. Now, I can tell you about these standards for diagrid buildings. So this was inspired by the Hearst Tower, which is located in New York City. And again, the question is like, how can we figure out the fundamental period? So one of the things that we did for design optimization is we're trying to minimize the number of elements that are needed in order for us to figure out what is the best performance. So we generated the FEM model, we determined the size of the optimization problem, initialized the design variables, and then we used the patented neurodynamic model of Adele and Park to be able to figure out what is the optimal design for each of these parameters. Now, the parameters that we were under consideration were basically the width, the height, and also the angle. So in diagrid structures, the angle is going to be very dominant because it's going to determine how many elements you actually need to be able to create it, and so on and so forth. So we subjected this with wind as well as earthquake loading, and we started looking at the performance, right? So this patented neurodynamic model has been used in the past for the design of structures, really large scale, and it's really innovative because it's learning as it's going. So as your design is being improved, then it's handling these nonlinear constraints really effectively, and it can guarantee that you're actually obtaining the optimal design and not somewhere in between. So these are the results. We started looking at different angles. So this is the different angles for the diagrids and looking at the minimization. So you will start with an original weight, with a particular number of variables, and then you actually start minimizing. So after iterations on the neurodynamic model takes place, you start minimizing the weight. And once you achieve a particular plateau, that's when you know that you have achieved the minimization of that. So we also looked at the angles and how that influenced the design, and also looking at, again, once you have those angles, you start looking at the density, and it's going to be one of big parameters. So we took a look, and Alejandro Palacio, he was the one that was looking at this particular project for a long time. He actually simulated over 200 buildings to figure out the performance. And then all of these are becoming, optimal designs for different kinds of configurations. And we started looking, okay, if you selected one equation that can describe everything, then this is one equation that can actually describe what you see in the figure here. But because we wanted to have something a little bit more friendly for the design guidelines, then we broke the estimation into 3 equations so that you only have the height as well as the angle of your diagrid as one of your parameters here. So we also started looking, so these are the one that is ANSE 7. So notice that the angle is not being under consideration. To have a similar look for that, we proposed this one, but then you have the second one, of course, the long version that is more accurate. And you can see the differences between those 3 with respect to the height and also the period calculated. One future direction that we're currently looking at is run by Garrett Demery. He's looking at the irregularity effects of the seismic performance of diagrid buildings. So not only looking at diagrids, but also when you have a particular vertical setback, right? And how could that influence the horizontal irregularity, or if you have setbacks, like how would that affect the actual performance. So that's up and coming. So stay tuned for that. Now, so far, I talked about some of the contributions that we've done during the assessment, the reconnaissance after an event. We are talking about what happens before the event, but then during the event, there's something that we have done as well, is this idea of smart structures, right? So how can we use smart technology to protect buildings from natural hazards? And this smart structures technology is something that is really interesting. So the idea behind this is that you can put sensors to monitor the health of the structure. So you could have sensors along the structure that is basically capturing the signals, right? So just like you will have in the medical, office, you could have a signal that determines that you have the health condition to be healthy versus not so well. Similarly, you can do the same for structure. So the idea is that you're capturing some information, either displacement or acceleration or some form of information from the structure. And that information is given to the computer, right? So in the computer, you're capturing this information and you're monitoring how it's performing. So you can see how during extreme events, it can be super important. In this particular tall structure, this is the Kenton Tower, the taller the building is, the more susceptible it is going to be for vibrations caused by wind events. But being able to design this also for earthquakes is also very critical. So being able to capture that information in real time and then being able to give some information to fight back, right? So we equip these kinds of buildings with actuation systems so they can adapt in real time. And that is given by actuators. So you have this kind of feedback loop where you're having some information from the structure, giving it to the computer, and the computer is doing something about it. So it could give the information to move left or right and being able to dampen those vibrations. And what that does is that it improves, the longevity and the response during an extreme event. So there are different types of structural systems that are able to do this. You have these passive structural control systems. And this is another example, the pendulum tuned mass damper that is in Taipei 101, one of the tallest buildings in the world. You basically, as a designer, you determine what is the length of these steel cables that are able to sway this 300-ton steel ball one way or another. And that's directly related to the fundamental period of the structure, right? In this case, you do not need sensors. All you have to do is just place the ball there and then tune it for one frequency, and that's it. Now, when you have an active mass damper, this is another example, you have a wider range of frequencies that you can adapt to, but it also requires some high external energy power, and you have to be active. And in this case, you have two active mass dampers that are able to sway in X and Y direction, and you have sensors that are capturing the information. Now, the best of both worlds is actually this idea of semi-active devices. And this is another example of the HIDAX, which is actually from the Kajima Corporation. And they have 72 of these installed in this building. And it's a wide range of frequency, but it doesn't require that much power to be able to perform. Now, the question is, if you are gathering this information from the structure, how do we adapt in real time? So when you're looking at structures, smart structures, you can think about your own sensory system, right? So we have sensors, we have information being processed, and that information is given to the actuators so they can move in real time. So this right here is one example of one of the first smart structures in the world where you have these three different variable stiffness devices. You have a computer that is you have the sensors, right? So the sensors is giving information for the computers, and the computers are telling the devices to move in one way or another, and you have an emergency electrical power source there as a backup in case you need it during an earthquake event, right? So that's basically the idea. Now you're gathering this information, and then it's giving it to the brain. So how does the building actually process the information and being able to adapt in real time? So there are different methodologies to do that. One way that we do that in our lab is actually using game theory. So game theory is the study of strategic decision-making, and it's the idea of using mathematical models of conflict and cooperation between intelligent, rational decision makers. So a lot of times when you think about game theory, that usually appears in economics, in political science, in biology, or in psychology, right? So this idea of if you're playing a game, right, the prisoner's dilemma, or you have some of these other examples, then you're looking at rational individuals. Now, if our building could think, and if as intelligent individuals, then we are able to create something that is able to adapt to a variety of different natural hazards, and it's able to have cooperation between actuators. So one of them, in case it starts failing, the other one can cooperate, and so on and so forth. So we adapted this technique or these game theory models and integrated it into buildings so we can have that sort of adaptation and give it some actual intelligence. So in order for us to make that happen, we combine 3 different concepts. So one of them is agent-based modeling, which is coming from artificial intelligence, this idea of decentralized control for the control theory. And again, one of the games in evolutionary game theory is replicator dynamics. And those are the 3 key ingredients for making this happen. So what I have a picture on the right is this idea of like, how do you define an agent, right? So an agent is something that can perceive something from the environment. And in this case, our sensors are the ones that are detecting the dynamic response from the environment. It is having some sort of reasoning, which in our case is given by the replicator dynamics. And then that reasoning is giving the actuators some direction, right? So it's giving some commands or actions so that this agent is able to make decisions in real time. So how does that look like? Well, in our case, we take a large structure that looks like this, and then we decompose it into different substructures. So each of these substructures becomes an agent, and they start exchanging information between each other, right? So when they start establishing this reaction, each of these subsystems will have its own set of actuators, its own set of information, its own set of sensors that is being informed, and then it's exchanging information between each other. When you do that, right, so each of these substructures looks like this. You have an input and an output. So in this case, the input is the earthquake that is being subjected. You have some displacements. So you basically take the equations of motion and transform it into what the state space configuration looks like. And then from here, you're getting some information from the sensors, right? So the sensors is giving it some information, like, for example, the floor displacements. The floor displacement is giving it to this replicator dynamics. So each floor, each F1, F2, and F3, right, they all represent the floor displacement or whatever state measurement you're thinking about, like acceleration, floor acceleration, for example. And then that information is being given to the system. Now, replicator dynamics, just like the word represents, you're trying to replicate a successful strategy. So when we're playing this game, we have one player that is always winning, the one that is actually at 0 displacement. So what's happening is that in this game, the first floor may be actually closer to winning, but the top floor might be the one that is actually displacing the most. So what happens is that you're giving it that information, and they're having this competition between resources that are available so they can win the game, which is closer to 0. So while this game is being played, this distribution of resources, so the actuator forces are being distributed across all these different devices, and that's what's capturing that minimization in terms of displacement or acceleration, whatever it is that you're deciding to do. So this is what's really interesting. And because it's such an innovative strategy, we implemented it on a 20-story building where we have 20 different devices across in every floor. We also started looking at smart base isolated systems. So that means that you have base isolation, but you also give it some actuators at different locations. So you're also being able to adapt to those configurations. So the difference between the first example and the second one is that this one is across the elevation, while this one is all at the base. So they present a different dynamics here. Another thing we did is that we took a bridge. This is actually an actual bridge in California that has been equipped with viscous devices. And we said, okay, well, if you have these viscous devices, what happens if you have semi-active or active devices? How would they behave? How would you distribute the resources? And we did that for that. We also started looking at these control rocking brace frames and then looking at optimization for that as well, looking at where would you place this, how would you design it to mitigate that, and using this technique for adapting to those. Now, we talk about the way it's going to think. Now, how is it going to be able to do that? So there are different types of semi-active devices. We have variable orifices, you have variable fluids, or you can variable friction. So in some cases, you're just opening and closing the valve. In some cases, like the MR damper, you can actually change the properties of the fluid, and that's the one that is actually causing those changes. But in the case of variable friction devices, you're actually changing the normal force. And that's the one that we thought it was really interesting, because when you're looking at variable fluids or variable orifices, you are relying on the fluid itself versus being able to just inject the force in there. So we got inspired by actually the bicycle, right? So if you notice the mechanism provided here, we can see that for each of the push on this, you actually have a mechanical advantage that is related to the length of the actual devices. So we started going on different prototype versions, and it has evolved, and now we're in version 5 or 6. And we started looking at how would we move the solenoid to be able to exert that normal force there, and seeing how the number of variable friction devices can actually perform that case. So this is what the prototype looks like in the experimental setup. So we have these different plates that are being connected with a friction in here, and then the device is actually exerting some information. So the idea is that for each of this, we'll actually have some information, and the load cell is capturing how much force is being generated. We have the displacement sensor is capturing how much is moving. So we have some setups where you're looking at 2 friction surfaces and one that has 4 friction surfaces. And we started looking at the performances when you have the passive off, right? So when you have the system in passive mode versus when you have it in passive on, which is completely different extension and how many forces are being dissipated because of that. So we increased the capabilities from 25 to 30 in this prototype, and we were able, when you have more play, to actually increase it more. So we started looking at, okay, so we have the capabilities to change that. So how do we actually modulate? So we started looking at on and off controllers, which is a common one used here. And the media is not playing for me right now, but you can see this is how the device is kind of moving here. This is ongoing work in our lab. We're really excited about the potential here. And then right now we have a theoretical mechanical advantage of 100, which means that for each of the newtons that is being generated, you can generate 100, which can help a lot with the capabilities and scalability of this particular technique. So we do have a cyber physical test setup where you have an NTS actuator, you have the reaction frame, and that is being moved. You have the sensors that are capturing the information, and again, the load cell and so on. So this is the new configuration, and you can see how we're able to validate the mechanical advantage of this. So for each of the sinusoidal waves, well, when you have it in a closed configuration, but when you have it open, you actually do generate that mechanical advantage. So we didn't get the 100 one that we get theoretically, but 78 is pretty good. So we're really encouraged to do that. And one way we can validate the performance is actually through this thing called real-time hybrid simulation. So if you were to model something in the computer and you have something experimentally, you use this technique to be able to validate how the performance is happening. And this requires this synchronization to happen, right? So you have this steel moment resisting frame, and then you're subjecting it to an earthquake, and then you want to see how this device is performing. So this is a way for having that interaction between the numerical and experimental substructure. Now, these are the different results from the experiment, and you can see how the semi-active is kind of moving and adapting to those changes. So we're really excited about that. These are the results from the displacement, right? So you have the uncontrolled one. So what happens when you don't have a device, and what happens when you do have the device, and in the open and closed configurations, and also the semi-active. So this is ongoing work that we're really excited about. And again, real-time hybrid simulation is definitely a cost-effective technique that we use to be able to validate different setups. So in this case, we had one device that we're validating, but in the future, we could have 3 of them, and then we can place them at different locations. And this is what real-time hybrid simulation can offer, because you're able to kind of place this device anywhere as long as you're setting up in the numerical model, and then you're testing it experimentally. And you can check out that publication regarding that synchronization, because you can see how this is an earthquake that is being, you're subjecting it on the computer, and then you say, okay, I'm placing this device here, then this node is moving in one direction, right? So you say, this node is moving to the right a certain distance, you're giving it that displacement to the actuator is moving this damping device in one direction. That load cell is capturing some information about it, and that's fed back to the system in that one time step. So this interaction that is happening between the numerical and the experimental substructure creates some delays in the system. So being able to address that delay is something that is very critical in RTHS simulations to make sure that you have this accurate performance. So that's another thing that we have looked at so that we can have this as accurate as possible. Another topic related to smart structures that we started looking into is this idea of cybersecurity, right? So we have these systems that have sensing, and we have control signals that are able to, make the devices move in certain directions. But what happens if there's a cyber attack, right? Like what happens if somebody comes across and then starts sending false signals, right, to the sensors, right? It's telling that it's moving, but it's actually not moving. And then it makes this active mass damper start moving. What happens then? And how do you mitigate that, right? So if you sense that there's an intrusion, how do you mitigate that? So this is where also game theory comes into play, because you're able to adapt and change the configuration. And this is something we looked at in this particular paper. So you're welcome to check it out. We do have some videos where you have, these two different devices that are moving in real time. If the attacker gets a hold of the bottom one, can the top one actually mitigate that change, and is able to actually do that? So we're really encouraged to continue to process this information. Now, another topic that is really interesting is this idea of aerodynamic mitigation, right? So we have heard about these adaptive facades that are able to change its shape based on natural ventilation and maybe solar energy and other things. But what really interesting for us is like, how can we adapt some of this technology for extreme events? So we noticed that there's a lot of damage to non-structural elements in tall buildings. So how can we actually leverage this information for adaptivity to make this more efficient? Now, the way traditionally this is addressed is looking at major or minor modifications. Major modifications looks at the overall shape of the structure, while minor modifications looks at the corners. So you have a square building, you could think about rounded corners, you can think about recessed corners, you can think about fins, and all of them have different ways to mitigate the aerodynamics that are happening on the building. Now, recently, we discovered that there were some researchers who were looking at the outer facade to actually improve. So instead of having that tuned mass damper, you can actually look at the outside facade to actually increase the weight, and we thought that was really interesting. We also looked at this other paper that had some Mori origami. And we were like, oh, that's so interesting that you can 3D print these triangle shapes, you give it an Arduino, give it some actuators, and they rotate. So if you give it some information, it starts getting these reconfigurations. So we were like, so we have this particularity. What if we actually put it on the building? So it goes back to the Hearst Tower here. And we had a researcher that started looking at what if the entire facade had these different configurations, and what we were able to push and pull and generate these different shapes. So if we were able to generate these shapes on the overall, building envelope, then how would you perform? So we started conducting some computational fluid dynamics, and we have some really interesting results that actually did show that you could reduce, we could improve a lot of the aerodynamics using this technology. Now, because it's really expensive to completely do a full-blown building envelope configuration, then we started looking at just the corners. So we had another student that started looking at what happened if you could deploy something on the corners, and you go between looking at a water bomb or looking at the existing origami patterns that you could actually deploy and seeing how those will perform. So these are the different shapes. So ideally, we were like, well, how close can these origami patterns actually achieve to the ones that are established in the literature in terms of aerodynamic mitigation? And these are the different results that the student came up with. That's Aaron Roffling. And he started looking at existing tessellations and how they could be adapted as a kinetic facade. So he started looking at some paper-based examples, then looking at these ideas of thick and rigid folding criteria, which is extremely important in mechanisms and origami designs. What that means is that, like, how far away is the thickness itself, right? This is no longer paper, materials have certain thickness. So when you're folding it, the spacing between them actually manages the stability of it and so on. So he started looking at that as well, looking at how these different patterns could actually fit in the corners. And then he also did some computational fluid dynamics to evaluate the performances of the different designs that he was exploring. And then we started looking at, okay, so you can figure out the origami patterns that you can put on your corners, how to actually make it move, right? So we started looking at these programmable materials where you actually engineer the material and being able to come up with different performance sets that you don't traditionally see that. So we were like, okay, how can we adapt some of this technology into the origami space? So we started looking at this rigid link configuration, and then we started thinking, okay, we're not gonna put actuators everywhere. So if we only have one actuator that is actually moving right to left, and we have different hinges that are different information, so rotating those hinges with lock and unlock mechanisms, how can we actually achieve the shapes that we're interested in, right? So the conventional approach is looking at one actuator per joint. It has a lot of energy to be able to do that. But the benefits of having that done is that you have a lot more control in terms of how you plan and how to create the shape you want. Now, because we are just looking at one actuator, we're thinking, okay, locking and unlocking of this joint, and then how can we actually generate this shape? Now, we don't know what shapes can be generated, and it might be slow to actually generate this shape. So how can we do that? So we started looking at the motion planning algorithm and how could we control it? So the way this works is that we have this chain mechanism. So we have an original configuration, and maybe we have this desired configuration at the end. So how many steps would it take for us to be able to achieve the desired configuration? So for that to happen, then we had to do this sub-slider crank approach. So it's basically unlocking one at a time, so you can create this slider crank and be able to move it around. So because of the sake of time, I just noticed that I'm going a little bit over. I'm just going to show you just really quick sort of what the slider crank mechanisms look like. You have a toggle position, so that's when you have it straight, and that's the area you're trying to avoid. So as you're moving left to right, there are only some feasible regions that you're trying to achieve. So we did the rapidly exploring random trees to be able to generate different configurations. So this is an algorithm that is able to learn as it's going, and how we can go from having just a straight line, you move it one, and then you see this configuration. Did you achieve the first angle? So you can see here, this angle right here, and then this angle right here. So you're able to achieve that by moving that node. You can start looking at different nodes. So the ones in green are the ones that are open, the reds are the ones that are closed, and so on and so forth. So for each of these nodes, you can actually identify until you find the final step. So let me just show you what it looks like. So in this particular algorithm, you start with a square and you go from triangular to chamfer corner to recessed corner. So this algorithm is able to go from one modification to the other. So this is what is really interesting, that we were able to capture, go from how can you have just with one slider being able to achieve the different configurations. So this is a collaboration project with Dr. Slava at University of Freiburg. And we did some prototyping and some experimental testing to test this idea. So this is what it looks like. So far, we have the triangle shape. So can they, by moving it from one end to the other, how can we achieve that? So we see how it's changing between those different shapes. And this is at 8 speed. This is still at the prototyping stage. There's still a lot to be thought of. Some questions here, of course, is like, this is all 2D. We are not looking at 3D yet. We don't know how the load bearing capabilities of this is there yet, but it's definitely an area that we're interesting. So in terms of design for exchange, what I just shared with you is a semi-active device that we're currently developing, how we're testing that, doing cyber-physical testing, the control methodologies using game theory to be able to adapt in real time. And we have some reconfigurable structures that we're looking at to explore these different mechanisms, as well as the vulnerability to cyber attacks. So we're really excited. I cannot do this without my amazing team. So a shout out to our Dream Structures Lab team, Alejandro Palacio Betancourt. He just graduated with a PhD, did a lot of work into this space. Suman Rocade, he was working on the lattice projects, and he is also pursuing a PhD in mechanical engineering. David Caballero Ruz, Elnath, and everybody else. This is a big team, multidisciplinary, architectural engineering, and electrical as well. If you are interested in this sort of vision for what the future looks like, I also invite you to check out the ACE, mega city, right? So in 2000, I think 92 or something like that, like what would a mega city look like in the future? And then the question is like, what technology can we develop now so we can get to that future? So I also encourage you to check that out. And without further ado, I'm gonna leave my website here, sotostructures.com, where we have a little bit of everything that I just explained today for the sake of time. But if you have any questions about what I just presented, I'll be happy to address them. And thank you so much for your attention.
Thank you so much, Dr. Soto. We really appreciate the presentation. And I want to open the floor to anybody in person or anybody on Zoom to go ahead and ask any questions. If you're on Zoom, go ahead and do the little like hand raise option if you've got it, or you can just unmute and ask a question. All right, yeah, go ahead. Yeah, just in the mic.
Can you hear me, Dr. Soto?
Yeah, I can hear you. I wonder if Noah wants to mute, like stop recording. I wonder if that will help people ask questions if they're not recorded.
Yeah. Here, I'll go ahead and pause recording. Okay. All right. Well, with all the questions over, thank you so much, Dr. Soto, for your time. I really appreciate the presentation. Is very interesting. And have a good weekend, everybody. Goodbye.
Absolutely. Thank you, everyone. I look forward to getting your emails and questions. Have a great rest of your weekend. It was great to visit your campus this afternoon. Looks great. It's sunny, beautiful. Take care.
And windy.